myself Dhruv Singh. I am second year CSE student at Tripati Kannur. Today I will be presenting a full classification model using ResNet implementation. So you can see the code on the lab. So I will be starting printing the code. So first I will tell you the aim of our project. The aim of the model is to, if I give an input of a food item image, then it can classify what item it is. It is a fruit or a bread or some other food, maybe cake. So it can be used we can integrate it in an app also and then create an application which will help us identify what food item we are eating right now. So you can see the code as follows. So first I have implemented the code using the PyTorch. So the first code block is the import the libraries. We have imported the torch and all the required libraries for the model training and model evaluation. This part of the code is for the defining the directory location for the data sets which will be used in the training. Now I have created a Python class of food dataset which will be used to get the dataset in an efficient way while training. So I have defined the path and all those things and the classes for the get item method which will help us to get the image and its label. So the size of the data that I will be using in the training has 16,000 images. So I have divided it into three sets: 9,866 for training, 3,430 for validation, and 3,347 for evaluation. Okay. So this is the class-wise count of the whole data set, right? We have 11 classes of the food item, so we have 11. It will be classified in 11 food items. All images will be either belong to one class out of all the 11 food items. So it is the overall demography of how many samples we have for each class. In all three sets. Now this is a sample image, as you can see. For visualization I have written. So images like these will be our inputs for this model. Now I will show you what model I am using. So initially I thought to use a normal CNN, but with that I wasn't getting a good accuracy. So I thought of using a ResNet 18 model, the basic ResNet of all the ResNets model. So what happened in the ResNet model, we use a residual connection. So what happens that when we apply a convolution operation on an image, we get some processed values. Now sometimes what happens, those processed values get very diminished. So we lost some representation of the image. So what we do in the ResNet model, that we take the original input and then apply a CNN, we get our processed values and then we add them with the original values, so that we don't lose any representation, any numbers because of the diminishing of the processed values. So in that way we get a better representation for our images, and then we send them into our neural network. As you can see, this is the overall layers and the number of convolution layers that have been applied. So we have first convolution block of 7 cross 7, convolution 2 block of 3 cross 3 max, 3 cross 3, two times we apply 3 cross 3 convolution operation. In third block we apply 3 cross 3 of convolution operation with 128 channels. In the same way, at the end what we get a total 1 cross 512 values. Now those values are transferred to a fully connected neural network. And at the end of the fully connected neural network, we have our number of classes, which will be used for classifying. Now this is the implementation of the model, the class of the ResNet team. So I have initially I have the block 1 here, convolution 1. Then I have block 2. Each block has two parts, 1 and 2. Two times we are doing the convolution operation. And you can see from block 3 we are starting to concatenate the convolution operation output and the original input. This is our definition part, so we don't see any operation being done here. Now the forward method. Here we see how this X is the input image. Now it is transferred first to the first convolution layer, then batch now is applied, ReLU is applied, and max is applied. Now from here, what we see, we apply a convolution layer, to this output, and background ReLU. So again convolution है background and dropout as the standard operations ReLU. Now here you see in ReLU I am adding the x11. X11 was, what was x11? It was the output of the previous block. So in this way, after applying, what is happening when I am applying the con211 and con212 on the x11, some values are getting too small after processing, that they are getting lost. So I am losing some information out of my image. So what I am doing, after getting this output, I am also adding the original input x11. So in that way, I am not losing any information, and also I am getting the better representation for the images which are required for classification. So we repeat this process for almost 5 times, 5 blocks we have done, and at the end we get our the final representation x52. We average pool it, and then we reshape it into one single array, and then we send it to the fully connected layer, that is the neural network, and we apply the ReLU and get the output. Now the definition of the model, the object of the raspberry model that are defined here, we create that, and this is the overall summary of the model. You see, this is a better summary. Yeah. These are the number of parameters that are at each layer, and you can see that. And at the end, the total trainable parameters are almost 11 million parameters we have total trainable parameters, and this is roll size. Now I have also looked for another parameter to check what is the how good or what is the characteristic of my model, that is the flops and max parameter. The flops and the G flops and the G max parameter, it will tell us how computational our model will be. So if higher the value of the max and flops, higher the computational requirement will be for my model. So I have also checked that, and then I have defined the optimizer and loss function. Loss function, normally classification we use cross entropy loss, so I have went with that, and ADAM is the standard good optimizer used in modern day applications with a learning rate of 0.0001. Now this is the training loop, and we give the input and output to our loss function and calculate the loss, and then call the optimizer function, and that way the loops work. You can see the output that I got during the training. I trained for 24 epochs, and at the end my test loss was 0.15 and training loss was 0.05. This is a better visualization for that training and test loss. So this is a training loss visualization. From it started around 0.27, 0.26, and then came to 0.05 around in 24 epochs. And this is a test loss. You can see that how it is different in the training loss and the test loss. In training loss it is just a normal uniform curve, but in test loss you can see it is not so uniform, it is going up and down because we are not training on the test set, we are just checking how the validation is happening. And then I use the inbuilt evaluation function from the torch eval matrix, and from that I got 0.67 accuracy on my model. But I didn't only check on this evaluation function, I also calculated the confusion matrix and then check out what are the measurement I am getting in my accuracy. So this is the confusion matrix for the model that I got from 1 to 10 classes. For each class, this is the confusion matrix, and for each class, bread, dairy product, dessert, all the food items, I got this one F1 score, recall, precision, and overall average precision I got 0.69, average recall 0.67, average F1 score 0.66. So I think the results can be made better with a little more fine tuning, or maybe you can say applying some augmentation operations and on the images, so maybe that can be improved.